find this integral. The integrand here is just y, where E, the region we're integrating over, is the solid bounded by these curves. So what we're doing is we're finding a triple integral over a region of y dv, where R is given by the region bounded by these curves. So R is bounded by these things. All right. So if I start graphing these, and it takes, the first time I started sketching the graph, I messed it up. So don't feel bad if that happens to you. It's not complete. It won't be as simple as I'm making it look now, because I've already done this. But I did it once. I'm like, oh no, that's probably not the right way to sketch it. I'll try again. So if you don't get it right the first time, don't feel bad. Let's see. In the first equation here, z equals x squared. That's just a parabola, right? So, oops. So here's the z-axis. Here's the x-axis, right? So z equals x squared is a parabola. And I'm going to put dashed lines back here because I feel like in the volume this is going to be behind. All right, I know that ahead of time because I've already done this. So here's this parabola. All right, z equals x squared. Y equals 0. Well, that's just that is just the plane. That's just the xz plane. So the back of this surface is just going to be the xz plane. So I'm not going to go anywhere behind this. Right. So all that stuff is out of there. And then z equals 12 minus 4y. Well, 12 minus 4y is just a linear function. That's in the form mx plus b, right? So that's just a line. It has z-intercept 12. So up here on the z-axis, I'm going to have height 12. And it's going to be a line that slopes downwards like this, and then comes and intersects the y-axis. Well, what does y have to be to make z 0? Well, y has to be 3. All right, so that's a line that intersects the z-axis at 12 and the y-axis at 3. And what am I bounding here? What region? Well, the back is the xz plane, so I'm not going anything behind that. I'm below this line. This is actually a plane. If we go off of the yz plane here and go and then include the x variable, you extend this in the x direction, you actually get a plane. So we're below this plane, but above this parabolic cylinder. So what I'm seeing here is you actually get, if you think about it, you get a shape that looks like this. This is the three-dimensional region. We're below this plane up here, but above this parabolic cylinder. That's this part down here. And with this problem, there's several ways to set up this integral. So here's one way to set it up. All right, you can say that, well, I think the easiest way to do this is to find the values of x that are on the x-axis below these two corner points here. And that's not immediately obvious, but after I started setting it up one way, I realized, oh, it would be easier if I did this. So find what these points are here. Well, that's not too bad, because you see this is a parabola z equals x squared, right? So I know the height here is 12, so 12 equals x squared. So I know what my x is. X is the square root of 12. And negative root 12 back here. So I'm going from negative root 12 to root 12. So for each x between negative root 12 and root 12, I am going, so if I take an x in here, what's my z doing? Z is ranging from this height up to here. Okay, now I got to rewrite the number 12 because I just scribbled it out. Okay, so z is going from here to here. So what's the lowest point? Well, that's a point on the parabola. So z is starting at x squared, right? That's what z was given by here, and going up to this line. Well, this line is just 12. So for each x between negative root 12 and root 12, z goes from x squared up to 12. Now, I've specified, for every x, I've specified a z. So now I got an xz. So now I have to find out is how far do I go out in the y direction until I hit this surface. right? So just going out in the y direction here, eventually I'm going to hit the surface. You know, how far do I go out? Well, that's given by this. So the way I've just kind of thought this out was x I specified first, so that goes on the outside. Then z, the z was the next thing I did, and then y I did last, so it goes on the inside. X I said went from negative root 12 to root 12. Z went from x squared to 12. And then y goes from, I'm going to let you fill this stuff in on your own, all right? And it's going to come from this, right? So you can see y starts back here and goes up to the surface. So you can figure out what goes here and here. And that will be how you set up that integral. But that's not the only way to do it. In fact, the first time I started this problem, I did it a different way before I realized, oh, wait, this way is a little bit easier. But let me show you, there's another way to do it, and it's not that bad. Naively, I first thought, oh, the most obvious range here is the 0 to 12 in the back. So I'm going to let z range from 0 to 12. Right? So I'll get a z in here between 0 and 12. And so that'll be my outer integral. So I'm outermost integral I'm doing with respect to z. And then for each z, I have to go to this curve and to that curve. And that's when I realized, oh, it might be easier the other way. But for each z, I'm going to this curve and this curve. Well, this curve comes from this, and I got to solve this for x, because I got to figure out how far out to go in the x direction. Well, x goes from up here. It's if you just solve this equation for x, you get x equals square root of z. And in the back, it goes to minus root z. So that was what my x ranged from. And then y, same thing, right? Y behaves the same way it did in the integral above. I just didn't like this because I don't like having roots to have to integrate. I just feel like that's yucky, right? So when I saw these roots appear, I said, well, stop doing it this way. I'm going to try to do it without square roots. And I'd rather be integrating squares than square roots. So after doing approach 2 first, I said, oh, maybe approach 1 would be better. But there's actually other ways to set this up. In fact, somebody in the forums posted an alternative way to do it, where they actually found x and y. I think they did x and y, and then the z was the last thing they did, which makes sense too, because you've already got this solved for z. Right, so there's lots of ways to set this problem up. This is just 2 of them. In fact, I think there's 6 different permutations that will work here. You can permute these x, y, and z, 6 different orders. And I think all of those, don't quote me on this, but I believe all of those will be doable in this triple integral setup.